Hello students, this is part 2 of lesson 2.
Today, let's learn about designating handedness using Fisher projection formulas.
First of all, what is Fisher projection formula? And why do you think it's important to learn that in biochemistry? Fisher projection formula is a two-dimensional representation of a three-dimensional organic molecule by projection. As a matter of fact, Fisher projections were originally proposed for the depiction of carbohydrates and used by chemists, particularly in organic chemistry and biochemistry. Now, why do you think it's important? It's important because Fisher projections are a convenient way of depicting chiral molecules, and it also helps us distinguish between pairs of enantiomers.
Fisher projection formulas carry the name of the originator, the German chemist known as Hermann Emil Fischer.
In a Fisher projection, it consists of both horizontal and vertical lines, as you can see in the diagram. If this diagram was drawn using the wedge and dash, the horizontal lines actually represent the atoms that are pointed towards the viewer, while the vertical line represents the atoms that are pointed away from the viewer. As you can see, the atom at the chiral center, which is almost always carbon, is not explicitly shown in a very long chain of Fisher projection formula. In the previous part of the lesson, I have mentioned that carbon is only considered the chiral center if the substituent or the four substituents bonded to carbon is different from one another. If the substituents or the four substituents bonded to a central carbon atoms are all identical, then that is not considered the chiral center. Alright, so this is how Hermann Emil Fischer looks like. Because drawing the three-dimensional representations of chiral molecules can be both time-consuming and very tedious, he developed the Fisher projection formula. Here are some examples of Fisher projection formula or structures. All of these are monosaccharides. We have D-galactose, D-mannose, D-allose, D-glyceraldehyde, D-ribose, D-arabinose, D-xylose, and D-lysose. What have you noticed? All of them are dextrorotatory. This means that all of these monosaccharides are right-handed. When I was still a college student just like you, my professor usually describes Fisher projection formulas like a fishbone. Now, look at the following diagrams. In the upper left molecular structure, you can see the chiral center number 1, which is in color red, and chiral center number 2, which is in color blue. Now, why do you think they are labeled as chiral center number 1 and chiral center number 2? Focus on chiral center number 1 first.
Please recall in our organic chemistry that in drawing the skeletal structure of organic compounds, we don't usually draw or write carbon. In every side of that zigzag lines you have seen there, that is considered as carbons. And sometimes the hydrogen atoms are not shown. But even if carbon and hydrogen atoms are not shown, it doesn't mean that they are not there. Okay, look at chiral center number 1. Look at the left side. I hope you can still recall your functional groups. The left side is a carboxylic acid substituent or COOH. And below the chiral center number 1, you have the OH or a hydroxyl group. Next, on top of chiral center number 1 is a hydrogen atom, which is not shown or which is not drawn. And lastly, the right side of chiral center number 1 is a carbon atom. Again, what is the criteria in examining if that carbon is a chiral center or not? The carbon must have 4 different substituents. In this case, the substituents of chiral center number 1 are the carboxylic acid, the OH groups or the hydroxyl groups, one hydrogen atom, and a carbon atom. Now, let's examine chiral center number 2.
First, look at the right side of chiral center number 2. The carbon atom in our chiral center number 2 is bonded to or directly bonded to a carbon atom, which is the chiral center number 1.
And you know that in chiral center number 1, it is attached to one hydrogen atom, attached to OH or the hydroxyl group, and attached to the carboxylic acid or the COOH group. Next substituent in the chiral center number 2 is the OH group above, and the atom below is a hydrogen which is not drawn or shown.
And lastly, the chiral center number 2, if you refer to the right side, you can see that the central carbon atom in chiral center number 2 is directly bonded to the carbon which contains the OH groups.
Therefore, the substituents of chiral center number 2 are first the chiral center number 1, and you already know the substituents of chiral center number 1. And the next substituent of chiral center number 2 is the OH group on top. And the third one is the hydrogen atoms below, or you know that it is not drawn or it is not shown. And lastly, the chiral center number 2 is directly bonded to carbon atom with OH group on the right side. Now, I want you to examine the remaining molecular structures by yourselves.
Just remember, the central carbon atom that you can see in the molecular structure will only be considered the chiral center if that central carbon atom is bonded to 4 different substituents. Now, the tetrahedral arrangement of the 4 different groups or substituents attached to the central carbon atom at the chiral center is governed by the following convention: the vertical lines and the horizontal lines. I have mentioned previously that the horizontal lines and the vertical lines represents the atoms that are pointed either towards the viewer or atoms that are pointed away from the viewer. Again, the horizontal lines represent the atoms that are pointed towards the viewer. In this slide, it mentions that the horizontal lines from the chiral center represent bonds to groups directed out of the printed page, and that out of the printed page is towards the viewer, while the vertical lines represent atoms that are pointed away from the viewer. And in this slide, it says that vertical lines from the chiral center represents bonds to groups directed into the printed page. Into the printed page means that the atoms are pointed away from the viewer. In Fisher projection formulas for monosaccharides, which is the simplest type of carbohydrate, the monosaccharide carbon chain is positioned vertically with the carbonyl group. A carbonyl group can either be an aldehyde or a ketone functional group, and they are located near or at the top. In this example, we have the smallest monosaccharide that has a chiral center is the compound glyceraldehyde. If we name this compound properly using what we have learned in organic chemistry, it will be named as 2,3-dihydroxypropanol. So, I hope you can still remember on how to name your organic compounds in organic chemistry. And please do not forget that it's also very important to be familiarized with the functional groups, as this will also help you identify the substituents attached to the central carbon atom. In this slide, we are shown that the Fisher formulas of the two enantiomers of glyceraldehyde are the D-glyceraldehyde, or the right-handed glyceraldehyde, and L-glyceraldehyde, or the left-handed glyceraldehyde. Do you observe the difference between the two? The CHO are both on top, and in the central carbon atom, we have the H and the OH, and below we have the CH2OH. Now, where do they differ? Look at the diagram carefully, or look at the structure carefully. They differ in the arrangement or position of the OH and the hydrogen atoms. In the D-glyceraldehyde, you can see that the location or position of hydrogen atoms is on the left side, while the OH group is on the right side. Now, let us look at L-glyceraldehyde. The OH group is positioned on the left side, while the hydrogen atom is positioned on the right side. Therefore, this glyceraldehyde is determined either as dextrorotatory or levorotatory based on the position of the OH groups that is directly attached to its central carbon atom, or which is the chiral center. Moving on, you already know that the handed mass of these two enantiomers is specified by using the designations of D and L. The enantiomer with the chiral center OH group on the right in the Fisher projection formula is by definition the right-handed isomer. In this example, we have D-glyceraldehyde. On the other hand, the enantiomer with the chiral center OH group on the left in the Fisher projection formula is by definition the left-handed isomer, or L-glyceraldehyde. Now, let us consider the compound 2,3-trihydroxybutanol. This is a monosaccharide with 4 carbons. That is why the parent name is butanol and 2 chiral center. For trihydroxy means that there are 3 OH groups attached to carbon 2, carbon 3, and carbon 4. The suffix "al" is added to the parent name butane because of the presence of CHO, and CHO is an aldehyde functional group. And thus, the parent name will become butanol, or the full name now will be 2,3,4-trihydroxybutanol. It has been mentioned here that 2,3,4-trihydroxybutanol contains 2 chiral centers. And remember, chiral centers have 4 different substituents directly attached to its central carbon atom. And because of this, there are 4 stereoisomers for these compounds, which means there are 2 pairs of enantiomers. Have you seen that 2 raised to the power of 2 on top is equal to 4 stereoisomers? That is because usually we only have 1 enantiomeric pair, and 1 pair is consist of 2 compounds. So, if there are 2 chiral centers present in an enantiomeric pair, then this means that you have to raise 2 to the power of 2. That 2, or the normal number 2, is the number of enantiomeric pair, and you know that 1 pair is only consists of 2. So, raised to the power of 2, that exponent 2 there, that is the number of chiral center found in an enantiomeric pair. Thus, this gives us 4 stereoisomers that are possible to exist. All in all, we have now 2 pairs of enantiomer. So the first pair is an
erythreose, or sometimes called erythrose, and the other one is a threose. As you can see, the enantiomeric pairs are mirror images of each other. So look at the erythreose and look at threose. They have a mirror image. Now, if a stereoisomer do not contain mirror images, then you call them diastereomers. Remember, enantiomers have mirror images, while diastereomers do not have mirror images. Say, for example, letter A and letter C. They are diastereomers because they are identical. They are not mirror images of each other. In the first enantiomeric pair, which is the enantiomers of erythrose, both the chiral center OH groups are on the same side of the Fisher projection formula. Okay, so look at the first one. The OH groups are both on the right side, while on the second pair under erythrose, you can see that the OH groups are both on the left side. On the other hand, the second enantiomeric pair, which is the threose, the chiral center OH groups are on the opposite sides of Fisher projection formula. So look at the first pair and the second pair of threose. They are on the opposite sides, while on the erythrose or erythreose, the position of OH groups are located on the same side of the first and the second pair. Remember, enantiomers always come in pairs. Just like our example, the first enantiomeric pair is the erythreose or erythrose, and the second enantiomeric pair is the threose. The D and L configuration used to designate the handedness of glyceraldehyde enantiomers is extended to monosaccharides with more than one chiral center in the following manner. The carbon chain is numbered starting at the carbonyl group. The carbonyl group in this example is CHO, and CHO is an aldehyde. The carbonyl group can either be an aldehyde or a ketone. So you can see that the carbonyl group is at the end of the molecule or on top, and the highest number chiral center is used to determine D or L configuration. In order to understand that, what do you mean by highest numbered chiral center? This means that the higher the atomic number of the immediate substituent of the central carbon atom, the higher the priority. Now, in order to understand this, what do you mean by the highest numbered chiral center? This refers to how we prioritize the chiral centers. So in this example, we have two chiral centers, and we only have to determine which between the two chiral centers has the highest priority. So in order to do that, you have to prioritize the 4 atoms or group of atoms directly attached to each carbon or chiral center, which is your central carbon atom, based on the atomic number of the atom that is bonded directly to the chiral center. The higher the atomic number, the higher the priority. In this example, the order of priority of the groups of atoms that are directly bonded to the central carbon atom or the chiral centers, from lowest to highest, we have hydrogen atoms, and higher to hydrogen atoms we have the CH2OH, followed by CHO, and then lastly the OH. That means the lowest. This means that hydrogen has the lowest priority, and the highest priority among the substituents are the OH groups. Therefore, between CHO and CH2OH, the higher priority is the CHO, which is the carbonyl group, and specifically an aldehyde group. So that is how you determine
which molecule is a D isomer and the L isomer. In our present example, compounds A and B is our first enantiomeric pair, and they are the D erythreose and L erythreose. And the compound C and D, which is the second enantiomeric pair, are the D threose and L threose. So this ends part 2. The next part will be uploaded later on. Please consider subscribing. Thank you!